Greetings. Good afternoon or good morning, depending on where you are. We are continuing with our thermodynamic lectures. My name is Professor Duke Orata. Remember last lecture, we had talked about heat transfer from vertical walls. And we are continuing with that to develop the heat transfer equations involving vertical walls. So let's just remind ourselves that the schematic for the vertical wall we had x-axis, we have our y-axis, we have our thermal, boundary layers, and if the temperature of the wall was TW, then of course it will continue decreasing. We had already discussed all this. And in terms of velocity, we have a maximum velocity, and then where it is zero. Remember, at the wall, the velocity is zero. Talked of the no-slip condition and so forth. So here we have Ts, and of course, this is the free convection maximum velocity. This is velocity, that is temperature. And so, of course, we have this x, the distance. Let's call this also our datum level. Let's call it also our datum level. Let's also use this as our datum level. And we say that at this point here, sigma is equals to sigma t. So that was a schematic which we had developed for the vertical wall. So we have our y-axis, x-axis, temperature at the wall, and then we have also the velocity profile. And we had said that from empirical and theoretical data, sigma over x was 3.93 into Prandtl's number and that we call the Grashof number, which, if you remember, we said that the Grashof number, we said it was mu squared. That was Grashof number. So we have just reminded ourselves where we came from so that we're able to move progressively. Again, as I always say, I humbly request you to follow this lecture systematically so that we build up, so you're not left, there's no gap as you move on. You fill in all those gaps. So we have just reminded ourselves of that. Now, we stopped at that particular point. Now we want to derive the heat transfer equations involving the vertical wall. Now remember, next to the vertical wall, we are talking about laminar flow. We are not talking about forced convection, which we have looked at in our previous discussion. We are looking at laminar flow. And so at the wall, that layer at the wall, there's no slip, so the velocity, like we have said, is zero, and then moves on up to where we have the free stream velocity and so forth. Now, we are saying that at the wall, the velocity is zero. So what does that mean? That means that the heat transfer in that section is not because of convection, but it's because of conduction, because of heat conduction. And the moment we talk about heat conduction, then it means that we have to use the Fourier's heat laws. Therefore, conduction heat conduction, heat transfer is by conduction, not convection. Therefore, we apply now the Fourier's heat law. And we know that from the Fourier's heat law, this diagram, you are now familiar with it, so we don't need to have it there. We know that the Fourier's law was Q is equals to minus K, the theta dy, and that terms of equation to the convective transfer, the H into Ts minus Tw. So if we call this theta, then that will be minus H theta S. Now, the profile, the thermal boundary profile, and the velocity profiles, remember we have said that both the thicknesses of the thermal boundary layer and the velocity boundary layer, when I'm talking about thermal, you can think of it also as the temperature boundary layer, is one and the same thing, are both equal. We say they're both equal because remember we had said that, earlier on we had seen that for this quantity, sigma over sigma t, when Prandtl number is 1, then sigma is equals to sigma t. So, we are working with these systems where we are saying that if we look at the temperature boundary profile, we had seen in our earlier derivations, in the earlier lectures, that they can be explained by a cubic parabola. The velocity profile the boundary layers can be explained cubic parabola. In other words, you have a parabolic equation which actually fits in that velocity profile. If you remember, just in passing, let's skip that because we'll use it. If you remember just in passing, we have said that for this parabolic profile, remember we had US, which is velocity, was 3 over 2, y was sigma minus a half y over sigma cubed. And we had also seen that for temperature, the time 3 over 2 y was sigma t minus a half y over sigma. So these are solutions which you are able to tell. For example, when you have y as being equal to sigma, for example, just as an example, remember when y is equals to sigma, then in that particular case, u over us will be 3 over 2 into 1 minus half into 1, and that will be 1.00. So u is equals to us. That's the velocity is the same as the free stream velocity. So this is something we are used to now. We have already worked this. These are parabolic equations. And even in this particular case, we will work with a parabolic equation to account for the heat profile. So in the case of the vertical wall, the parabolic expression is parabolic expression, you have theta, or theta s equals to 2 over sigma minus y sigma squared. Sigma is just the boundary thickness. That's the boundary layer thickness. Don't forget the boundary layer thickness. So we have that case of ours. Just don't forget. We have our boundary layer thicknesses. For example, we have a boundary layer thickness. Sigma t, for example, is that. That's our boundary layer thickness. Don't forget those quantities. This is x, this y. Notice that when you're dealing with the vertical wall, that is our x for the vertical wall, and our y is that. So don't forget the two profiles. It's just to remind you of the thicknesses of the boundary layers. And of course, when we had for velocity, remember we had about the same. Now it was like that. Again, the thickness where the free stream, that is sigma t. Let's look at the two differences there. But now if you go through our lectures systematically, then you will see when we develop the profile for the thermal boundary layer, we develop the profile for the concentration boundary layer, and of course for the velocity boundary layer. So I kindly encourage you once again, just go through those lectures. Now, if we rearrange this equation, which is a very simple exercise, if we rearrange this particular equation, then theta is equals to 2 y over sigma theta s minus y over sigma square theta s. We'll truncate our analysis. We'll truncate them to the first term. Let's just truncate our analysis to the first term. In other words, we forget that particular term. So if you take that derivative in the Fourier expression, take that derivative in the Fourier heat law, remember Q, we said it was minus K, that's Fourier heat law. We say that d theta over dy is equals to minus h, and we call that theta s. So let's get the derivative. Therefore, if you take the derivative, dy, for this particular quantity, remember, just remind yourself that identity which you're using there, derivative of xn, the x will be nxn minus 1. Don't forget that. So we have just used that. That's the identity we are using, which we'll use here. So what do we have? We'll have 2 theta s over sigma. So if you take this quantity here, which you have gotten, after taking the derivative of this quantity here, taking the derivative of this quantity, we will get 2 theta s over sigma. So we can substitute that into the body of the main Fourier expression, so that we have Q is equals to minus K 2 theta s over sigma. And that is minus h theta s. So of course, if we simplify this quantity, the theta s's, that is the changes in temperature, will cancel out. Therefore, we will have h. H will be equal to minus 2k. We have k there, h minus 2k, that cancels out. H will be minus 2k over sigma. So that's an important expression which you have gotten there. Now, you remember in our earlier lectures, again, just can we go through them? when you remember earlier lectures, we said that the Nusselt number was HL over K. Don't confuse that with the Stanton number. Stanton number was different from the Nusselt number. The Nusselt number is HL over K. So if we substitute this quantity into the Nusselt number here, substitute it there, our lives become easier, a lot easier. So what do we have? So substituting the transfer coefficient H into the Nusselt number, we have now, and the Nusselt number will be H, that is minus 2K over sigma, that is our H. Let's call that X instead of L, because we're dealing with the length in X direction. Now X there divided by K. And so that will be minus, there should be no minus here because they have cancelled out. So we don't need the minus there. This minus has cancelled out. Here they both have cancelled out, so we don't need minus there. So we have, that would be 2x over sigma. That is 2x over sigma. Now, we need space here. So if we go back to our expressions, our early expression, which we had said was sigma over x, which we had gotten was 3.93 PR minus a half into PR plus to the Grashof number minus a quarter. We even got it here. We've already written it, we don't need it. So, if we use that quantity, if we use this particular quantity, I want you to notice that this is sigma over x, that is x over sigma, is inverted. So if it's inverted, what does that mean? What are we saying? If we have x raised to power, just that identity, just note it, raised to power half. If I invert it, I take 1 over x to the half. It is basically x to the power minus a half. And so we are going to be able to, when we invert these quantities, the minuses will now become plus, and the plus will become minus. And of course this, because has no index, it will be 1 over 393. So if we convert this to, therefore, x over sigma in this particular case will now be 1 over 3.93 PR half into PR minus a quarter, and the Grashof number, the power fourth root of that. Fourth root of that. And this is our expression now, which we have here. So we have that this sigma x is equal to x over sigma into 1 over 3.93 PR. In that case, because remember, we have said our Nusselt number, we have said was hx. We had our Nusselt number here, which was HL over K. And so we have already put our quantity for H, which we have here, which we had gotten here, that is our H. From that expression, remember, we had already cancelled those two quantities. We had 2k sigma into H, and we have already put in those particular quantities. And so this term here, when we now have our H here, remember our H here once again was H is equals to 2k over sigma. So when we put our H there, we now had our Nusselt number was 2k over sigma x 2k over sigma, then you have x over k, the k is cancelled out. So we have the Nusselt number is 2 times x over sigma. And that x over sigma is what we have here. And so let's plug in those particular quantities and see what we get. Very simple. So we have just rearranged this quantity, sigma over x, in terms of the Prandtl number and Grashof numbers. And once we have rearranged them, like we have said, we have just inverted them. So that minus a half becomes plus a half. A quarter becomes, the index a quarter becomes minus a quarter. Minus a quarter, that index of minus a quarter becomes plus a quarter. And so we have this expression. So the Nusselt number will be quite bulky. Therefore, the Nusselt number now becomes quite bulky. We have 2 over 3.93 Prandtl number per half number plus 20 raised to power minus 1 over 4 Grashof's number 1 over 4. And so if we make our life, we can make our life easy by rounding off this particular quantity. So if we round off this particular quantity to 4, so if we approximate that 3.93, just say 3.93, approximate it as 4.00, then the Nusselt number now is 0.5, number half, PR plus 21, minus a quarter, yeah, quarter. And it's important to remember these things. Prandtl number, we know that the Prandtl number is the dynamic viscosity divided by K. Reynolds number, always remember, the Reynolds number, remember Reynolds number is density, velocity, displacement length, and dynamic viscosity. These are very important quantities which we have now worked. And we know also, don't forget that the Grashof number, we said we have mu square. These are important quantities which you need to always remember because you keep working with them. And you keep working with them, so you should be able to reference them on very short notice. So you need to always remember these particular quantities. So what are we saying here now? Now the Nusselt number, remember, in the case of forced convection, we have said that the Nusselt number was a function of the Prandtl number and Reynolds number. But now you see that in this particular case of free convection, we have it as free convection here. We now have the Nusselt number is a function of the Prandtl number and the Grashof number. Very important for us to note that. It's a function of the Nusselt number and the Grashof number. And of course, remember, just always remember that we say that the Nusselt number divided by the Reynolds number and the Prandtl number give you the Stanton number, give you that Stanton number. And that is very important for us to note. That was the Stanton number. So in simple terms, we have just built our discussions on the vertical heat transfer involving vertical wall to what we have done in the past. We have just used the parabolic profiling of the boundary layer and proceeded just in the same way, using the aspects that near the wall where the velocity is relatively zero. There we are going to have conduction not by convection, transfer of heat as a result of convection, but as a result of conduction. And these are concepts which you have built and you continue to build upon them. So I keep encouraging you that you go through some of those discussions which you have had as you are building up this particular concept. So let us stop at this particular point. We are going to pick up from there next time.